I'd like to welcome everybody to our first fall 2023 meeting of the IMAG-MSM Working Group on Multiscale Modeling and Viral Pandemics. It's hard to believe that we're starting another year. I really appreciate everybody's ongoing interest and commitment in this group. It's not often that these kinds of groups last as long as they have. And so we really are grateful to you for being here today and for your enthusiasm and participation. As always, I need to remind you that this meeting is live streamed on YouTube and that an edited version of the video will be made available publicly so that people can see the work that's being discussed. As always, Tom Helikar and myself, Jim Sluka, and Lorenzo are available to take your suggestions, comments, and criticisms. We welcome ideas and suggestions and look forward to trying to make things work better. In particular, if you have ideas about how to make our seminar series more successful, we'd appreciate that. We have a variety of social media channels. I guess we have to change the name Twitter to something else now, but in particular, we have the wonderful IMAG MSM wiki page. We have an IMAG LinkedIn page, and there is a YouTube channel, which has our archive of seminars, more than 100 of them. We'd love to have your help with that. We have a Twitter hashtag MSMViral. If you can help us publicize the seminars in advance or after they're recorded, we would very much appreciate that. It's a wonderful repertory of material on a wide variety of topics related to viral infection, immune response, and multiscale modeling more generally. We very much appreciate your help getting the word out. As people know, at the beginning of the year, we set up a nonprofit called the Global Alliance for Immune Prediction and Intervention. Tom Helikar has been working furiously trying to develop this. We'd appreciate content for the website. We'd appreciate ideas. We're trying to arrange to hold a first annual meeting of this organization, growing out of the working group. And anyone who would like to participate in that, help us build that, have ideas about the format, where to hold it, that would be much appreciated. Are there any other announcements before we continue? Traditionally, the steering committee meets the day after the working groups, but we've somehow slipped a week. And so officially, our steering committee meeting will actually be next Friday, this 1st of September, rather than tomorrow. We may try to rearrange things to put them back in sync once that happens. So we'll see how that works out. Coming up, we have talks on September 7th and 21st. Francois Grenier is going to be talking about his work on trying to understand SARS-CoV-2 origins. We have talks by Tongli Zhang and Yufeng coming up, and Bruce Lee. We have an open slot November 2nd, so if somebody would like to suggest a speaker, that would be great. As always, you've heard me say the same thing many, many times. Suggest yourself as a speaker. Gary today has spoken many times. Just because you spoke once doesn't mean we don't want to hear about updates on the current project or on other projects you're working on. Please suggest your graduate students, postdocs, people who've published recent work that you'd like to hear about. Any suggestions that you have, please send to us or use this Google form. We really do appreciate your ideas for how to make this working group seminar series a success. So today we have Gary Ann, who's going to be talking about synthetic data series and AI. And I will turn the screen share over to him.
Great. So thank you for the opportunity to speak on the umpteenth time. I am pretty much giving the similar-ish type of talk. Most of you have heard, or many of you have heard parts of this before, But the backstory for this particular talk has to do with this kind of ongoing theme in this working group, which is trying to find an intersection between the mechanism-based multi-scale simulation type models that we make and we all love, and the wider community that is enamored with machine learning and artificial intelligence. So we've had this conversation extensively within both this venue and others regarding some of the barriers that us as mechanistic modelers have to overcome. And this particular talk has to do with finding a potential use case where we can aid the people who are AI and data-centric in doing the things that they want to do within the context of what other people in AI and other domains do. So that's where this idea of generating synthetic data comes from. This talk has to do with a very specific circumstance in which this can be done, but I think very impactful. Right. So what this talk is about is specifically about how to generate synthetic data to augment multiplex molecular level time series to help train AI systems, right, for a variety of things that AI systems want to do. And the reason that this is important is that invariably, when many of these AI projects are talking about using existing clinical or demographic or histological or EMR-based types of data, at the end of that almost always comes some promissory note about incorporating some biological fundamentals associated with that, some sort of biological data. And as we are becoming more cognizant of the importance of needing to think about diseases as trajectories and not just as individual states, the time series component of that is important. But to try and do that, we're using some of the more classical methods of generating synthetic data has certain challenges associated with it, and I would say fundamental limitations and restrictions on what you can do, and therefore that's the focus on this particular topic. Adjacent to that is there's been much talk about the use of or development of medical digital twins, which are inherently personalizations of computational models. And there's also a analogous issue with respect to how do you train a artificial intelligence or machine learning system to disentangle individual trajectories out of a population level data set, which is necessary to do the training. So I put this paper in the chat. This talk is essentially just a summary of this particular paper. So if you want to sign off and just read this paper, that's fine. But if you don't like the paper and want to interact with me and tell me that I'm wrong, then that's what this venue is for. Okay, so synthetic data. So I think everyone who does any sort of serious AI or ML realizes that synthetic data is necessary and a key to any sort of modern application of ML or AI, right? And in industrial applications, this is being done. It is heavily used in image processing, et cetera. And as you can see here, the ability to generate synthetic data is becoming an industry in and of itself, particularly from an AI standpoint through the wider application of generative adversarial networks, which are partially related to the large language models that are coming around, but this is a little bit different than specifically that, right? But if you do AI or ML in any other domain, the idea of using synthetic data to augment your existing data is almost a necessary part of your workflows. The question is, how can we use that in biomedical AI and ML, and in what circumstances are the ways of generating synthetic data okay, and in which cases, which are they maybe not? Right. So what are the classical approaches to generating synthetic data? So the primary one is using statistical methods, including machine learning, artificial neural network-based methods. Right. So statistical synthetic data can be generated if you have enough real-world data, so you can have a statistical distribution that you trust, that is real. And you can use classic statistics there for that, or there's enough data that allows you to train a adversarial neural network to look through the noise that you add on to find what the invariant is, what the ground truth is underneath a particular learning approach, right? But as this little next part says, in order for that to work, you need to know what the ground truth is. You need to know what the invariant is, et cetera. And in image processing, you have very large annotated data sets that say this is a cat and not something else. And therefore, you have some target, right? Some known identifiable invariant that allows you to say, this is the thing that you are separating out all the noise that you add on to learn that function from the thing that you're trying to identify, right? So because you have large annotated data sets that have a metric of ground truth, image generation has been very effective in this particular domain. The other way to approach synthetic data is using physics-based approaches. And when I say physics-based, I mean like real physics, like laws of physics type of thing, where you use mechanism-based simulations where you have some sort of a ground truth, foundational natural law, or defined operational structure for how that particular world works that is rock solid for purposes of creating the environment that is now your synthetic environment. So, for things like self-driving cars, physics-based models will work for that, for driving the environment and seeing how things actually interact. And also games kind of fall into this category as well, because there is a ground truth associated with the rules, because the possible configurations of the world are constrained by the rules of the particular game. All right, so in these particular circumstances, you can essentially create a virtual world in which your AI will operate and interact, and therefore you can create multiple configurations that are grounded in this particular world, those set of world rules that will vastly expand your training data. So reinforcement systems very heavily rely on these types of circumstances. Right, so those sorts of things sometimes work in biomedicine, right? So lots of people are using AI and generating synthetic data in biomedical applications. And, it's pretty obvious that biomedical image processing, either radiologic or histological analysis, really falls into the same category as general image processing, where you have an invariant that's established through a relatively large corpus of annotation and all that type of thing, and it allows you to use your classical GAN type approaches to generate synthetic data. In a semi-analogous and maybe a little bit more limited context, population level data in terms of large clinical data sets, I mean like really large, like thousands of patients large, are used to generate, essentially assuming that sample sufficiently represents the breadth of the variables that you're looking for in a population and the distribution of those variables in that population. You can use statistical methods to create synthetic populations that are used as control populations in many sort of in silico trials that are being done in industry. So this is, again, a very a prevalent sort of way of generating synthetic populations, which is consistent with how other domains do that. And for physics-based systems, this is again very similar to the difference between physics-based biomedical simulations and cellular molecular simulations. When you have a representation of your particular system that's grounded in physical laws, then you can create a trustworthy simulation of that particular object and use that to explore multiple configurations that, again, are constrained by the laws of physics, et cetera. Right, and that's applicable for these biomechanical models, flow dynamics models, and such. So, however, this thing that people want to add to their data sets to improve the predictive capability of their AI systems, which is essentially molecular level data. And when I say molecular, it's the very generic term of a molecule. So it could be proteins, circulating mediators, genes, gene expression, RNA, et cetera. Whatever molecular entities you want to say or include, the things I'm going to talk about apply to this type of data. And this is, even though a very, very constrained type of data, because it's not images, it's not physiologic signs, et cetera, it is molecules, right? Levels of molecules. This is the vast majority of what experimental biology is nowadays, right? I mean, 99% of all biomedical research involves looking at the levels and responses of certain molecules that are used to characterize particular states of biological systems. Right, and the entire molecular biology, cellular biology research endeavor is predicated on this premise that more granular knowledge about how those systems work, right, is a way to improve health, right? And this is what's driven the improvement in, the advances in technologies to look at finer granularity with respect to the molecular profiles that determine biological state and are assumed to affect biological function. Going along with that, drug development is essentially predicated upon the idea of identifying molecular entities that will affect these molecular systems in a way that is desirable. And the supposition, again, is that more granular information about these systems will give you a way to identify more effective, targeted, and efficacious and robust therapeutic agents, which are molecules in themselves. Right. So, but these two driving, forces in biomedical research run into significant problems if one wants to create synthetic data that correlates to what the experimental biologists are actually doing. All right. So the first thing is that statistical methods won't work because there is perpetual data sparsity, right? And we all have heard about the curse of dimensionality, right? About the amount that that there's an exponential increase in the number of samples you need to be able to identify as you start adding variables. And what is molecular biology but adding variables to your description of the system, right? And already as we have it, the number of samples that we have to represent the space of biology in this multidimensional space is really far behind and lives in the curse of dimensionality. And therefore, the driving force in biology runs exactly into this particular problem. So the idea that you are getting a sufficient representation of the distribution across a multidimensional space by any sample that you have is inherently flawed because you don't, right? Because it's always too sparse, right, to be able to calculate what the true distribution actually is. So what if you don't know what the true distribution is? You make assumptions about the distribution, and one of the most common things is that people assume a normal distribution. right? So the assumption of a normal distribution is predicated upon the fact that the central limit theorem is applicable to the system and the measurements that you're taking. And the fact is that for the vast majority of multiplex molecular time series data, the normal distribution cannot be assumed because the central limit theorem does not hold, right? These are not independent variables. They affect each other and their distributions. And the sources are not random because you're sampling almost by definition people that have a different distribution because you're looking at individual pathological circumstances, right? So you can't assume a normal distribution, and there's actually multiple reports in which normal distributions are not present when they try and get enough dense data to try and do this. So you can't do that. So you see very often that people will assume a normal distribution when they're trying to create, a synthetic data set, a particular molecular distribution, and it's just not a valid assumption to make, right? So you can't do that. You got to do something else. Physics-based models won't work because of the discussed previously issue that when we're talking about the mechanisms associated with cellular molecular biology, there are no corresponding fundamental laws that constrain what sets of behaviors they can have in a useful fashion. And that last part is important because obviously they're physical systems. Obviously, they are bound by the laws of physics and thermodynamics, et cetera, but those are not descriptive enough to actually characterize the multiplicity of states that are of interest in terms of the biology that we're looking at. Right. So when we don't have fundamental laws to fall back on that govern cellular molecular biology, then we don't have those. And therefore, we have to kind of do induction. And we know that induction is, always incomplete. And the fact is that we can't know everything. And we are therefore operating in a space of perpetual, epistemic, incompleteness, and uncertainty. So we can't describe everything. We know that, and we need to figure out a way how we operate in that particular space. Sometimes people are trying to use machine learning methods to try and parse, right, how things actually work. But when we're talking about cells and molecules and biological systems, these things are inherently generatively hierarchical, meaning that interactions between certain molecules will lead to different types of cellular behaviors, and that's one hierarchy. And then aggregated cellular behaviors are non-linearly related to how tissues and organs behave. That's another hierarchy, right? So we're talking about generative hierarchies here. And within the AI field, within the machine learning field, this is part of Judah Pearl's initial description of causal inference. There is a limitation in the ability to evaluate generative hierarchical causality when you cross hierarchies, right? And it has to do with the fact that there are too many degrees of freedom for a particular data set, and it is impossible to identify causality across a hierarchical boundary given a particular data set. This is in some ways related to the unidentifiability problem, which is a separate issue, but it's present, right? So since you can't use ML or AI to do that, right? You can't use any of those causal inference-based approaches to do that. And we're operating in the space of perpetual epistemic uncertainty. What we would like to be able to do is to operate over some space where we are minimizing any bias that is made by the person who makes the mechanistic model, right? So I will, quote one of my most hated quotes in mathematical modeling, which is the box quote about all models being wrong. I mean, it's not like it's untrue, but it's unnecessarily pejorative. And I think the key is that there are necessary abstractions that need to be made whenever someone makes a particular model of any sort, right? And those represent a choice. Those choices are going to bias anything that comes out of that particular model, and that moves you away from any sort of truth that you're trying to have in a generalizable fashion, which is particularly important when you're trying to create synthetic data to train an artificial neural network, which is designed to find an answer for whatever it is you do, right? So I'll get to this maximal entropy principle in a second here. So if we are, and again, this talk is focused on specifically generating synthetic data to train AI systems, right? There's a way that you can generate synthetic data like epidemiologic data or using ordinary differential equations that can allow someone to gain understanding about how that system actually works. But that data can't be used to train an AI because the AI will see through anything you add to it and you'll end up with the model that you have underneath. And then if that's the case, why do you need the AI, right? So if we're trying to create synthetic molecular time series data to augment the capabilities of an AI, we need to know what the limitations of those systems actually are. And one of the major problems with neural network-based AI systems is they fail to generalize, right? And this is, again, an extraordinarily common phenomenon. Everyone knows about it. And it is the discordance between the training environment and the implementation environment, and that term is called data drift. Right. So if you are trying to overcome that, right, that's part of the reason that you're using synthetic data, because you are then having a wider breadth of a representation of possible configurations of the world that the AI is now trying to describe. Right. Any sort of SMT that you come up with should be as expansive or least biased as possible to cover the breadth of configurations that this particular system might reasonably be expected to have in the real world. Right. So that's one thing that you want to be able to how to overcome if you're creating this data, synthetic data, because if you don't, then you're just going to have a brittle, overtrained AI. And the other challenge that you have with AIs is they have difficulty with discrimination unless the data sets explicitly can separate that. Right. So many AI projects are classification tasks or regression tasks where there's a supposition that there's some difference present between the two classes that you're trying to identify. And again, in biomedicine, it's very easy. Do they have the disease or not? Is it getting worse or not, et cetera? Right. So the major problem with existing time series data sets, and I'll show you an example in a second, is that there is no difference for if you look at it in the way that we're interested in terms of forecasting an individual person. So here's an example of a graph from this particular preprint. I think it may have actually been published since then, but this is host response cytokine trajectories in COVID-19 patients based on different levels of ventilatory support. And the context is not important because this phenomenon that is seen in these three plots, representative plots from this particular preprint, is exactly like any sort of time series data anybody ever looks at, right? And if you looked at these things, you know exactly what I'm talking about, because if you look at each group and you calculate their mean, you can find a difference. Okay, and that's very useful. You can say, oh, yes, there is some sort of fundamental difference between these particular groups that exists somewhere. But that's not what we're trying to do when we're trying to forecast how an individual patient is going to be, right? What we actually want to know is if I have IL-8 at this value, which group am I actually in? Right. And you can't distinguish between those because you don't know what the other context happens to be. Right. So I've asked people if there is actually a statistic that tells you the group membership likelihood based on these distributions. And I've not heard anything. Maybe someone can come up with an answer for me. Right. But this is actually the clinical question is I get a test. Right. I get this particular value right here. This value is present in all four of the groups that we have. Which group is it actually in? And I want to be able to project in the future which thing it's actually going to be in. So this is intrinsic to the digital twin question. This is intrinsic to any sort of forecasting that you want to do based on these particular values, because these means are ex post facto generated, right? You can't partition that in that way, and ideally, what you would like to be able to do is you would like to say, okay, I have sets of trajectories, because not every single point in this cytokine space is reachable by every other point. It is constrained in some way, shape, or form, but what is that particular constraint, right? And what are the possibilities of those particular future histories of a particular, of a system given a particular point in multidimensional space? So how do you deal with those sorts of things when you're generating synthetic molecular time series data? So the first thing I would propose is that you are choosing a sufficiently complex abstraction value level, right, for your mechanism-based simulation model. And I'll talk about why I think you need to have a mechanistic model. I think it's inferred because you can't do it by data. So if you don't have data, you have to do it by mechanism. In order to use that particular model, in order to capture the breadth of possible trajectories, at some level, we want to kind of rethink about what parameters are in your model. And the way that I'm thinking about it in a biological sense is that those parameters represent the differential levels of responsiveness of a biological system with respect to the molecular pathways that you happen to see. In order to avoid data drift, right, in order to avoid any sort of biases that are present by what you have chosen to represent in your computational mechanistic model, you want to maximize the expansiveness, right, of the generated set of potential trajectories by incorporating acknowledgement of the uncertainty and the incompleteness that's there when you do that. And that's what the maximal entropy principle says, right? And these things put together create an alternative idea of what calibration actually means. So this is the proposal, right? A proposed method for generating synthetic molecular time series is to use a mechanism-based multi-scale simulation model based on existing biological knowledge that is chosen, right? And this, again, is very commonly a negative that is placed against people who do this type of modeling, because they say, well, you left stuff out. How do you know you left the thing out that wasn't important? And there's no answer to that unless you do something like this, right? The use of the simulation model partially addresses the curse of dimensionality because you can simulate millions and millions and trillions of patients if you need to do so, right? So you can't actually meet, right, the curse of dimensionality, but you can approach some rapprochement with it by being able to, via orders of magnitude, increase the amount of potential trajectories you have, which is the whole point of synthetic data. The multi-scale nature of the model overcomes the limitations of the causal hierarchy theorem because you're actually generating it, right? It's not something that you're trying to infer. You are producing as embedded in the mechanisms in your particular model, how you have those hierarchical relationships. And each of those represents a testable hypothesis, what we'll get back to later. And the way to address this idea of bias about what you chose to leave and leave out is a way of dealing with the parameter space of this model in a functional sort of way that encompasses all this possibility by maximizing the set of configurations that will fit a particular data set. All right. And this goes to the idea of non-falsifiability as a keystone in being able to minimize bias. So inherent to this is the idea that these simulation models are data guided. They're not data driven, they're knowledge driven because you come up with a model that's based on a particular knowledge map, right? But they are guided by a data distribution from the real world. Right now, you acknowledge that sample of the real world probably does not represent, almost certainly does not represent the entire breadth of possibility across the human population, right? This is data sparsity issue. The question is, how do you operate with your model to, in a believable and rigorous way, encompass what is already there that we know the biological system can actually generate, and amplify that in some way, because you recognize that just because you're outlier in your sample set doesn't necessarily mean that that's the outlier for the biology, right? So the idea is then, if you operate over that entire space, and if you compass the breadth, a wider breadth of what humanly is possible, then you are anticipating the possibility of data drift, because now you're encompassing your entire range of possibility, right, with your SMT. So this is the mathematical object that was come up with by my colleague Chase Cockrell about how to think about the parameter space of a mechanistic model in a way that essentially represents the differential functional responsiveness of these systems, right? So this little schematic talks about how we think about representing these models very often as a set of entities or mediators that interact, and they produce some particular process, et cetera. And the fact of the matter is that the vast majority of the molecular wiring in a particular cell represents essentially the tuning of these kinds of molecular processes. So if you think about those aggregated sort of interactions, they can be considered as parameters that represent the responsiveness of the represented particular things that you have put in your model. And here's another example of this, right, where the model rule matrix is a matrix of all the rules that are present in your particular system and all the entities that you've chosen to represent. And when you write down this matrix for the model when you start, it's going to be sparse, because there are things that aren't necessarily connected to other things when you write down that particular model. Now, in biology, everything is connected to everything else. So there's probably some indirect effect, right, of that entity on something else. You just haven't either described it or explicitly represented it, but kind of know it's there, right? So the idea is that this, for a particular knowledge structure, gives you a way to represent what your starting matrix is. That's going to be relatively sparse in the interaction you chose to represent. But as you do the calibration process and you fit to a heterogeneous data set, or not fit, but kind of are guided by a heterogeneous data set, then this matrix becomes more complex. So I'm going to give you an example of this. And this example is using a digital twin, which is our innate inflammatory response model here, which simulates sepsis. And we used it to, we operated over a data source of trauma patients from the U.S. Services Health Services System, SC2I TDAP protocol, on trauma patients, looking for those that developed acute respiratory distress syndrome and those did not, right? And the data type is down there. A wireframe diagram of the model is up here in the right corner. Those details are not important, except that if you look at that particular model, every single box represents an entity across the top, right? And each particular arrow represents a rule down the left column. Even if you create an MRM of this, the 17 mediators and 25 rules, this is what the base model looks like in terms of sparseness of interactions, right? And the color there has to do with the value of the parameter of that interaction. So separate talk, but we have a multi-machine learning pipeline that uses a combination of genetic algorithms and active learning to find all the possible configurations of this particular matrix by modifying the non-zero elements, or the zero elements to non-zero elements, to identify which ones, configurations of this model cannot be falsified by that data set, meaning that it's not saying it's true. You just can't say it's not true because that model is able to reach the data points present in your clinical data set. And as you can see on the right side here, that is what an evolved example of an MRM looks like after a series of iterations. For people who think that that means you can say anything you want, you actually can't. It does have a constraint on the structure. It's just really, really large, right? So here's a heat map of the value levels for each particular component of the MRM, and this is a 3D depiction of that. So it's extraordinarily large. It's just not infinite, which is kind of what you need to operate over. So then we take that and we say, okay, now we have this particular data set. Let's see what all the trajectories are that are possible given this particular non-falsifiable space. So what we're looking at here is one particular cytokine, tumor necrosis factor, right? And we're looking at a comparison between the real data points, which are the blue, which are the non-ARDS, and the red, which are the ARDS, and any trajectories that might be present, which are the dashed lines, right? And what are the possible configurations of the model that fit these 2 points? Now, on the back end, we do separate MRM calibrations to the ARDS versus non-ARDS, right? Because as if you would do with the means, there is a difference between those patients, but you can't necessarily distinguish them by looking at their points. So these shaded areas represent the trajectory spaces of these 2 different calibrations, these two different sets of MRMs. And as you can see, they overlap a lot, which means that if you were just looking at it from a data-centric standpoint, that if you looked at these, a point in this particular in TNF space, you wouldn't be able to tell, right, what it's in, unless you're in these outlier components here. But since you're generating a trajectory, there's information then in derivatives associated with these slopes, right? Those are the things that an AI and a neural network can find. So the premise is that by creating these very rich trajectory spaces that are partitioned, right, that the neural networks will find, right, particular properties of their trajectories that would be able to distinguish between one versus the other. And this is the whole idea of the forecasting cones that we think about when we talk about forecasts of chaotic or stochastic systems. From the multi-scale nature of this, so these are 2 examples of other cytokines with similar properties, right? But we're now linking them to a higher order phenotype, essentially tissue damage, by linking them to tissue damage that's produced in the model. And then you see this in the lower graph, right? Again, this is a sanity check to show that the configurations of those particular sets of MRMs in each set actually produce different system level phenotypes corresponding to a clinical finding. All right, so the benefits of this particular approach, right, we kind of addressed them a little bit earlier, is that simulation generated SMT produces data at a scale and density and coverage that is not possible, right? And this whole idea of being able to have very granular trajectory information to be able to, for the neural network to find. Inherent to this process is that the breadth of the MRM and the stochasticity within these particular models obscures the generative model. And this is really important because if you talk to anyone who does AL and MI, you say, oh, I have an ODE that's going to create synthetic data. I'm like, I don't care about that because they'll just find the ODE. And the same thing, if you do a classical stochastic differential equation, you'll look past your noise term, it will find the underlying function, right? And if you have that particular function, you don't need the machine learning thing because it's not real. So the incorporation of the MRM, MEP, and the stochastic components of it is intended to obscure, right, the biases in your represented model and somehow achieve greater truth. Okay. And because of the way that it's constructed, it's encompassing the heterogeneity, the intrinsic heterogeneity, the real heterogeneity that's seen in these populations. So how do we know it's right? We don't know it's right. How do we know it's going to work? We don't know it's going to work, right? But since the basis of this is a knowledge-based model that we can analyze and pick apart, if it doesn't work, it provides a grounds for useful failure moving forward, because everything generated by these models is a testable hypothesis. So this is opposed to a standard data reliant GAN, because if it doesn't work, you don't know why it didn't work. All you can say is that data that you had was not representative, my invariant was not chosen correctly, etc. All right. So being able to iteratively improve is a substantial benefit of these types of systems. Less related to, formally generating synthetic data, the advantage of a mechanistic model is that you can do things for which have not been tried before. So these are the whole area of trying new drugs, testing new drugs, combinations of drugs that haven't been tried before, or repurposing it into a novel context. And this last one, I think, is really important and is kind of hard to, isn't necessarily intuitive, but it can overcome biases in existing data sets. So let's assume that you have an underrepresented population that may have kind of a little bit of a different, set of molecular trajectories. There's not enough of those particular samples, for whatever reason, to be able to say that that's representative of the entire population. But if you use this particular method, right, you can fill that out and you can overcome the bias in the sampling by creating equivalent numbers of simulations there, right? So this is the balancing, part when you do ML, where you just don't want it to just guess based on the incidence in the population, right? That's not what you actually want to do. You want it to be able to find what the generative function is that explains the data. So you can balance the data in a much more unbiased fashion by creating simulations of this type and synthetic data of this type, right, by fitting to even relatively sparse numbers of underserved or underrepresented clinical populations. Right, so what are the next steps? So the low-hanging fruit is to see whether or not this actually works, right? What does this type of synthetic molecular time series data actually improve the performance of a ML AI system? So we have a grant, we just got one, to test this in the prediction of sepsis in the post-burn population with the USIS group that shared their trauma data with us. Dr. Shobel McHugh and Dr. Cockrell are the PIs on that particular project. And hopefully this will be a demonstration case that this is true, where we are going to essentially compare classical prediction models from one institution against other institutions, and then augment that with synthetic data generated in this fashion. The additional use case for this, which I think we would try to be able to make a pitch to the Bridge to AI group at the NIH, which quite rightly focused on data standards and that type of stuff. All right, but thinking ahead about how synthetic data is necessary for everything else, right? Whether or not there is some place for us to play in that particular environment, get access to that data, and then have circumstances where we can do head-to-head competitions against existing algorithms. We would be interested, Dr. Cockrell and myself, be interested in working with other groups to adapt this idea of the model rule matrix to other systems. And this is a adjunctive but integral component to the idea of medical digital twins, because again, it is improving the ability to predict and forecast individual trajectories, which is the whole personalization component. So thank you very much for your time, and I'm happy to take any questions and critiques.
Thank you very much, Gary. That was great. The floor is open. I've been allowing people to unmute, but I'll give everyone unmute privileges. So please unmute, turn on your camera, unmute, ask away, please. Grant, go ahead, please.
Sure. Let's see, turn on my camera. That might be a problem. Let's see. Did it work? There I am.
Yes, I see you.
Yeah.
Hi.
I was trying to fight the temptation to ask a question with the idea that I better read the paper first. But my initial, of course, I was a little bit taken aback with the slide that said, why didn't statistical methods work? Because to many people, statistical methods is a large subset of what I consider them to be. And then you went on there to say, people assume the CLT. Well, not necessarily. There are lots of ways of choosing distributions that might mimic the data better. And now I'm trying to understand then this matrix, but essentially, so some of the things you were saying that it's sort of like spike in a way. Some of the synthetic approaches are spiking truth in and adding noise. And the problem there is you don't know the extent of the noise, right? So
That's right. You don't know what the ground truth is, right?
Yeah, that's the other thing. So the signal, you don't know even the signal. But then the bigger problem is also you don't know the extent of the noise. So if you generate noise, how large should it be? And that's going to affect your inferences you make. But then you went on to say that, this doesn't work, that doesn't work. But then it looks like your model is based on simulation and, model based at some level, right?
Yes, it is.
Yeah, okay. And I was thinking that, what was I saying? Oh, the whole idea of sparsity, or I'm trying to understand how the matrix, how does it, well, one thing I'm trying to deal with is when you said, if you try to basically fit the model that generated the data with AI, then it'll spit back the model you started with to generate the data. But that's only if you are in the, if you're not in the high dimensional setting. The neural nets and all of that suffer from the high dimensionality in exactly the same way that maximum likelihood does. Or say it's a regularized regression or model averaging. They suffer from
some mathematically compact generative function, right? Like an equation or different, like a differential equation.
Right.
Right. So those are great questions. So let me start, with the statistical thing.
Mm-hmm.
So I recognize that not everyone assumes a normal distribution. And actually there's a question in here in the chat from Mitchell Colbank, which I think is analogous to this, that there are a whole multiplicity of distributions that you could choose,
Mm-hmm.
that you think might fit your particular data distribution, right? And there are methods to try and come up with that, and my response to that is, well, that's a choice, right? There are multiple ones that are possible. You don't have any idea about which one is actually the real one, right? There are a whole bunch of them that you could try. And it is only afterwards, whether you collect more data to see whether or not that particular distribution is trustworthy, that you could say, okay, that was right or that was wrong. Right. But you have no option other than trying to see whether or not it seems to work. And then if it does work, then that's okay. And if it doesn't, or until it's not, and then if it doesn't, then you have to pick something else, but you don't know exactly why the one you chose isn't the one that works, right? You're just cycling through a set of punitive distributions that you think might be there. Right. And that's what people do. And that's what and this is where the useful failure component comes out of it, is because if you are wrong with a model that is based on a punitive mechanistic knowledge structure, then you can go back and look at that knowledge structure and say, yeah, this thing over here, I'm not quite sure this is the thing that works or not, because it essentially gives you a hard target upon which you can evaluate the performance of your particular ML algorithm. Now, this is related a little bit to the question about obscuring the generative function underneath, right? So part of the example is the efficacy of machine learning to reconstitute fundamental mathematical and physical laws, right? So there are papers in which people extract the equations of deterministic chaos out of chaotic systems. They extract the laws of cosmology out of these very noisy types of systems, et cetera, right? And the reason they're able to do that is because we know that there is that equation that represents those particular systems, right? So if you go in the other direction and you say, I have an equation and I add a whole bunch of noise to it, et cetera, we know that based on how these things have performed in the past in the other direction, that it's going to find that equation, right? And if it's going to find that equation, then you don't need the machine learning model to do it unless you're,
I understand the point, but my experience in looking at simulations in maybe a simpler setting, but nonetheless complex enough to encompass things similar to this, is that sparsity is always going to be a problem. So a machine learning method, even if it's if the data generation is specified in the way you say it, with a distribution of a known form, the neural net, say with 2 hidden layers or so, any number of hidden layers, any kind of situation is going to run into trouble with sparsity in that multiple solutions are possible. And, maybe, with regularization in lasso, for example, one solution is possible, but, if you generate the data set again, you're going to get the range of possible models being fit exceeds, say a central quantity that should represent a constant distribution plus noise plus error. In a nice setting, we would have a well-posed problem with more data points than parameters. We would get a point estimate of our parameters, and then we would have a confidence interval. But in a sparse problem, whether it's neural nets or regularized regression or model averaging or what it is, we're going to end up with the point estimate itself is a random variable. And so So
the use of the simulation is an escape from that circularity, right? Because the problem with using statistical ways to generate synthetic data that is then going to be used to train what is essentially a statistical model is that those sorts of biases will percolate through. By creating, imagining, not from a statistical distribution, but how these things actually potentially are generated, a much wider set of possible configurations of that system that are present in your sparse data, then you can potentially have a separate loop, where you have this generative function, that is not statistical per se, but then you can do statistical analysis on it because now you have many more points to identify whether or not that actually is going to be. The key here.
Sorry, go ahead.
All right. The key here is how do you, quote unquote, calibrate or fit that particular model, Because the classical way to do that is to consider the points of data that you have, the sparse points, And you try and either draw a line through them, fit to a mean, or you treat those points as boundary conditions for a parameter space for an equation-based model. Okay. But if you think about what those points actually are in biology, right, it means that a biological system in some particular way, through some particular configuration, assuming there's no measurement error, was able to generate that particular point. We don't know how it was able to generate that particular point, but it was able to generate that particular point. We also have a reasonable supposition that we have not lucked out, that we've picked a particular point that is actually a boundary condition over the possibility of that particular configuration. So this is where this model rho matrix comes in, because what it does is it says, okay, I'm going to run 1,000 stochastic replicates of this particular configuration of the model. All I want to know is whether or not one of those stochastic replicates is able to reach this particular point, right? Because then you get a very large cone or some cone around that particular point that represents a larger representation of the possibility space of that particular configuration.
That was the picture about the sparse matrix, and then the one how you get to the colored in one, which
that's right.
represent the possible, and so you have all this possible variability.
That's right.
I'm still, I don't know, maybe I'm stupid, but I still think that whether or not your data comes from a model that has a central, some sort of parameters, or whether it's generated in the way you're talking about, still, if you're dealing with sparse data and you throw it at a neural net or whatever it is, then then you project down on some nice low dimensional characteristic, like the probability somebody's going to progress to respiratory failure. The thing you're going to get out of it is not stable to a point. Like if you were able to generate the data over and over and over again, the more I think about this, and the more, the more I sort of map out these ideas, that characteristic is itself a random variable, and depends upon, and so it's a moving target, basically.
Well, so if you just look at the data points, yes, I think that's true. But the fact is that it's not random data points, right? They are points along a trajectory. And as I've noted, not every particular particular point is reachable by every other point, right? So the trajectory is constrained by the knowledge structure of the model that's used to generate that particular trajectory. And if you have the data from the trajectory, of which you cannot do other than just a series of straight lines, because you have no idea about what the intervening time series dynamics are of the real world system.
So you're saying that the sparse data that we have, the real data that we have, sort of constrains, in a way, the possible corners of the large space that could have generated it.
Right. And it's extraordinarily large, but it's not infinite.
I got it. Okay. Now I got to go read that paper. It's extremely interesting. Thank you.
Thanks for your questions.
Okay. Any other questions? Don't be shy about it. I mean, I think, Gary, my problem always with trying to formalize rules in the way you're doing it here is how you handle situations when you have large numbers of interacting signals that have to be integrated. When the rules separate, when you have separation of variables in a physicist's way or a mathematical way, then the formalization of rules is relatively easy. When you have very complex integration of signals, the way you do, say, in a gene regulatory network, where you could have 20 different things coming in, some of which are, if they're ands or ors, it's easy. But if there's some more complicated integration of signals, then it's difficult to come up with a formalism that lets you break those down in an orderly way. And so I always struggle a little bit with just the representation of complex signal integration in rule systems.
Yeah, so of course that is true. And one of the limitations of the current iteration of the MRM is the nature of the relationships that these entities can have within the rules is arithmetic, right? Where there could be a more complex sort of interaction between those sorts of things. And I think as we, so currently this base model is being evolved into something that incorporates more complex relationships, and that will be, something that we can deal with. On the other hand, you can do a lot with arithmetic if you add enough, features, right? So while that is a legitimate, I think a very legitimate critique, I think as a starting point, the density of the sets of interactions and the variability and the values that they can have and all the multiple configurations they have operating on top of a rule structure that you've specified, that actually gives you a very broad coverage of what the possibilities are, right? So it's not just, propositional logic. It's not Boolean, right? Because there is, gradations in it. But that's still a big jump, right, from a Boolean network to something like this.
Right. I didn't mean it as a criticism.
I understand. We've had this conversation before, so yeah.
Any other questions for today? Well, I really appreciate people coming back. It was nice to see so many new faces. I'm delighted Gary was willing to come and talk about this because it's a very fundamental question. And I look forward to seeing the steering committee in a week and many of you back in 2 weeks. Thank you so much. And thank you, Gary, for being willing to kick off the fall.